Electron affinity. So you can kind of think of this as the opposite of ionization energy. Electron affinity, which is generally symbolized as EA, is the energy change when a neutral atom in the gas state gains an electron. So ionization energy is the energy needed to remove an electron. Electron affinity is what happens when a neutral atom gains an electron. So we can write an equation for that. The neutral atom plus an electron gives us M minus, so a -1 anion, plus EA. Now that electron affinity, that energy change is usually negative. It's exothermic, so it's releasing energy, but it can be positive. So all of the noble gases have positive electron affinities. Why might that be? So that's the equivalent of, okay, I'm gonna give, well, as I'm the noble gas, somebody's giving me an electron and they have to pay me to take it. Yeah, because they were in a good place to start with. They are happy where they are. And if I take that on that extra electron, it's not going to work anymore. The kids don't fit in the minivan anymore, right? So this is, you got to pay me for my trouble. So most of them are negative, meaning I'm getting an electron, I pay you some money for the electron. But some of them are positive. Alkyl and earth metals sometimes do that too. Because they want to lose an electron, they don't want to gain one. It's going in the wrong direction, right? Electron affinity trends are less regular than the other trends. So we do see a trend that the electron affinity decreases. It becomes more positive as we go down group 1A. Other groups don't show this trend. It generally increases, becomes more negative across a period. But I'm not going to test you on this one because I can't give you two elements on the periodic table and say which one's got a higher electron affinity. The trends aren't strong enough to do that. The highest electron affinity in any period, highest meaning most negative, because that's confusing too, would be the halogens. Because the halogens want to gain an electron, right? When they gain an electron, they're getting their noble gas electron structure, and so they're going to pay the most for an electron. So that's really about the best thing you can remember. So there's a table showing the different ones. And when it says greater than 0, it just means that it's positive. You have to pay that atom to take the electrons. And then we get into metals and nonmetals, and this is more clear cut. So this is a side-by-side list of properties of metals and nonmetals. And so we can look at the metals and then say, well, the nonmetals are not that, just like their name suggests. So metals are malleable and ductile, and those are two words you might not be familiar with. Malleable means it can be pounded into a sheet, hammered flat. Ductile means it can be drawn into a wire, and those are properties of metals. Metals are generally shiny, lustrous, they reflect light. Again, these are general properties. There are exceptions. Metals conduct heat and electricity. Their oxides are generally basic and they're always ionic. They form cations in solution and they lose electrons in reactions. They're oxidized. So the nonmetals are the opposite of that. These are like identifying characteristics of someone who's masculine versus someone who's feminine, stereotypical gender qualities. You can say, well, this person is more like this stereotypical ultimate masculine person, right? Or this one's less. But there's a continuum there, right? And they're just general properties. Not all metals have to have all of those things, and some of them are more significant than others. And so we can talk about, as soon as my computer here catches up with me, we can talk about trends in metallic character. There we go. So what's metallic character? Well, how closely do the element's properties match the ideal properties of a metal? So with human gender, we could say, well, how masculine is that person or how feminine is that person? Now you could compare two guys and say one's more feminine than the other. Does that mean they're female? No. It just means their characteristics are more towards that side of the continuum, right? So metallic character, we're looking at, well, how well does it match up with that ultimate list of metallic properties? And I think this is actually the very easiest trend to predict. Metallic character decreases left to right, and it increases down a column. And if we look at the periodic table, it's just like almost jumping out at us. So if we go across a period, here's sodium. Is sodium a metal or a nonmetal? It's right here. Here's our line. Is that right? Yeah. Yeah, everything to the left of the red line I just drew, those are metals. So metal, 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 silicon's a semi-metal, non-metal, non-metal, non-metal. Am I getting more metallic or less metallic as I go across? Less. I'm actually going from metals to non-metals, right? And going down, I'm going from non-metals through the semi-metals into the metals. So, yeah. That one's pretty easy, I think. Again, here we've got the, in the purple, those are the semi-metals. These are all non-metals, and these guys are all the metals. There's a lot more metals than non-metals. But if you need the trend, all you have to do is pick one of these that's kind of in the middle. If you're looking down here, that's not going to be helpful, or if you're looking down the column over there, that's going to be tough. But just pick one of these, and you can just very clearly see what the trend is. So on the basis of periodic trends, choose the more metallic element from each pair. I don't know if you've noticed, but a lot of these things are the same elements that we've been looking at before. So here's germanium or tin. Well, tin is more metallic. Tin actually is a metal, and germanium's a semi-metal. So, there's that. So tin's more metallic. Gallium or tin. So here's gallium or tin. It's like the optometrist, which is better, lens 1 or 2? 1 or 2. I always stress out. I'm like, I'm going to make a mistake and I'm going to get the wrong prescription. It's very stressful. Yeah, this is the one we can't really tell because going across it gets less metallic, but going down it gets more metallic, and so these trends oppose each other. And then these guys are, like just diagonal, and they're right lined up with this. I mean, if I had tin here and then chromium, this is way far away from the semi-metal region. I'd predict that the chromium is more metallic than tin, even though tin is lower. But here it's just, they're both one away from a non-metal, semi-metal, and so can't tell. Can't tell. Lead or not lead. So you could very easily answer the wrong question. Phosphorus or bismuth? Bismuth. Because bismuth is actually down in the metals, and phosphorus is really a non-metal, so that's not so hard. But then we can look at boron and nitrogen. Let's see what's a color I haven't used. There's boron and nitrogen. So as I'm going across, they become less metallic, so that means that boron is more metallic. If I looked at like sulfur and chlorine, or maybe fluorine and chlorine, they're both nonmetals, right? They're not metallic. But which one is more metallic? Chlorine. Okay? And then this is a separate section, but I'm not going to make it a separate video. It's a table showing a summary of these trends. So good to refer to. I'm not going to give you this table on an exam. Sorry. Yeah, well, then there's this thing called an open book test or a take-home test. And students are like, oh, yeah, great. But the questions are way harder, right? And so it's not a good thing. It's not a good thing.